the computer science and technology here at Cambridge has the unenviable task just before lunch of talking to us about how AI might revolutionize conservation practice. Thanks, Anil.
Thank you, Simon. And might I say how impressed I am that you sitting there wearing a shirt and no jacket here shows just how robust and rugged you conservation practitioners are. As a computer scientist, I'm used to being in a nice warm place. And listening to Tiago and Julia right now, talking about how much work goes in the field into finding these nuggets of causal evidence and spending thousands and thousands of human hours and human lives coming up with little bits of knowledge. And it struck me just how precious this knowledge is, because it represents just a huge collaborative movement that, for example, in this university, we have spent hundreds of years convening lots and lots of the people involved who gathered this kind of natural science and performed the natural experiments. And what we've traditionally done is to take a bunch of the people and to communicate by the process of publications. So we run these trials, we run these surveys, we perform experiments, and we write them up as papers that we publish. And in Cambridge, we have a copyright library. So this means that every book published in the UK with an ISBN is available and accessible. And so we can draw on a vast amount of human knowledge in order to then perform things like systematic reviews, in order to look at the large scale of what is going on. We can then run kind of tactical, short-term literature surveys on individual topics, for example, for a new PhD student. And then ultimately, whenever search engines became a thing about 25 years ago, we can also have very effective indexing of things going on. So this has been good, and it's been progressing solidly over the last few centuries. And then a couple of years ago, we've had this crazy AI wave. And I say this as a computer scientist who's used to having a very rapid progression of technology. And what's happening in AI and the rate at what it is changing society is incredible right now. And we've seen that we've shifted away from people looking at the literature as the primary source to using systems such as ChatGPT as their primary mechanism of inquiring about some source of knowledge. How many people here have used ChatGPT just to ask it questions and so on? So over half of the audience has done this. I just came back from India yesterday, and all of my cousins in India are just using ChatGPT instead of Google now to get things. And there's a reason for this. It's because it's really seductive technology. It allows you've got a friend who talks back to you immediately with seemingly perfect recall. You can interactively explore very, very complicated social scenarios because the LLM seems to have a built-in view of what human culture involves. It understands the nuance of languages, and you can frame some pretty complicated scenarios. So this is kind of a good thing, it seems. But as with many of these seductive technologies, we're facing a choice right now. And 2026 is going to be the year where we have to decide whether we take the red pill or the blue pill when it comes to AI. The red pill is black box AI. So systems such as ChatGPT, Google Gemini, just absolutely incredible frontier models. But when it comes to using them as a source of an evidence base, you start to discover that they have certain undesirable properties. They can seemingly give you the right answer, but the way that it came up with the answer is opaque. The results change weekly if you ask it the same question again and again. They seem to be beautifully articulated, erudite answers, but they're wrong. And when you think about the effort that goes into the systematic experiments that we're running in the field of conservation, how underfunded the field is, it's offensive that we can build a technology that can just not only point you in not a random direction, but the wrong direction in a very confident way. You start to realize just how harmful some of these technologies are. And of course, because they're based around individual kind of corporations, the results are irretrievable and not accessible widely as well. The second choice we have is, instead of having black box AIs, we can have human augmentation mechanisms. That is, we keep experts in the loop and we make the practice of your field faster, better, and cheaper without ever replacing the human being. And the technology is very much the same, but there's certain properties we want. We want the results to be traceable, so we know exactly where a bit of knowledge came from. We want reproducible. We want the same answers until we change the inputs. We want to make sure that this information is accessible widely, and that we can verify independently the results in order to conduct the kind of scientific rigor that we've talked about throughout the rest of this morning. And so what I'm going to talk about here is our program, which we call the Technology for Living Evidence, where we combine observational factors such as remote sensing or all the various ground data that we have, and also then say, well, how do we take the causal factors, but the things that we know, and then combine these two things to form something that is greater than just the sum of its parts? And in order to do this, we want to build technology that isn't just solving individual problems, but we want to bake in the blue pill into the very fabric of the technology so that it, from day one, is designed to be used by conservation practitioners for positive human augmentation outcomes instead. So I'm going to tell you quickly about just two of these bits of technologies, and hopefully we can hear more about what you need as well to help us guide our work in the coming year and make sure that we can solve problems that matter for good conservation outcomes as well. The first one is something that Julia mentioned, something called Tessera. And whenever I got into this field about 5 years ago, we thought we could solve the world's problems using satellites because it's an incredible technology. You could just look down at the world from space and you get a full view of what is going on. But the problem with satellite imagery is that it's quite a lot of work to use, because in order to get something done, you need to figure out how to download vast amounts of data. You need to manage it all, and you need to then account for a temporal signal, very important in conservation to know seasonality and so on. And so what we did with Tessera was ask ourselves, can we train an AI model that takes in a lot of data, but preserves the temporal signal in such a way that it can be useful for reasoning about how a system that we're looking at from the sky evolves day by day. And what we did was we took Sentinel-1 and 2, which are satellites run by the EU, and their outputs are completely public, so anyone can download these things. And we trained a model that looks at a single 10-meter squared tile across all of the world's terrestrial surface, and it learns the repeated observations that happen over a year on that one space. So instead of just taking one picture of a field, we take, say, 150 over the course of a year, and we order them in such a way that they're ordered by time, so that the system has almost got a video of what happens over winter through to spring and summer, and then learns about how crops and so on grow there or whatever is happening there. And you can see here some of the beautiful pictures that come out of this. So instead of coming up with just a visual three-dimensional picture, we come up with 128 dimensions. So instead of RGB, we have 128 numbers that represent whatever happened in that space. These numbers have no meaning, but then you can train systems that give them meaning by providing ground truth. So if you want to do crop classification and so on, you can figure that out. But just before we get into that, you can see how there's lots and lots of really nice looking pictures here that show you the rich structure that you can get from looking at this. So this is Cambridgeshire. You can see Cambridge over there. These are all false colors. The colors mean nothing, but the difference in colors just shows you just how much discretization you can get by looking at one of these, and you can zoom in all the way down to a 10-meter squared tile. So we've taken what is a lot of data and compressed it down into these small little tiles that have a ton of semantic information built into them that we can then use, all from publicly available data. Now, how many of you have done GIS processing before? Have you done remote sensing? So I see about maybe a quarter of you have done that before, and it's very, very labor intensive. The problem is you need to do this for every single task that you have. You might be doing land segmentation or land use or many of the habitat maps we've heard about this morning. But for each one of them, you need to go through the same process all the way from getting the data to processing it. The idea behind Tessera is that we can amortize this by spending a lot of energy to train this thing just once. And because we train it and we give it away, about 99% of the compute power required to train this model has happened and is then given away in an open and a globally downloadable way that is reproducible by anyone else. So we've got a few other people around the world who are currently redoing our experiments and generating their own version of it just to check that it's safe and solid. And then once you do that, you require very little energy to then apply it to any other kind of geospatial tasks. So if you wanted to, for example, figure out canopy height, you can just download the region of interest that you want, And then you can just train a very simple model that can, in many cases, run on a mobile phone and run offline that will just do exactly what you need. And then you can spend your time on the difficult work of validation. That is checking that the inferences that have come out of this model are actually meeting the ground truth that you want to find as well. So the idea here is that we can find a large number of tasks, and we can just have a single global, open, reproducible, and traceable model, which can be reused and composed in order to tackle hundreds and hundreds of downstream tasks. So we're looking at trying to figure out how do we not only just make you 10% faster, but how do we speed you up by an order of magnitude, and in such a way that it can work anywhere on the world's terrestrial surface. So if I'm in the middle of Botswana, in the field, I can download the tiles for Botswana to my phone and use that in order to do quick on-the-ground analyses, and then bring it back into this part of the world to figure out how to make it all work. So this is one example of how we can use technology to use publicly funded and openly available data in order to provide a service that can then be used to accelerate the observational aspects of conservation. The second one is we started looking at the literature because there's a huge problem with AI poisoning happening right now. And with AI poisoning, the problem is that we have hundreds of millions of papers published, and we're trying to figure out, well, what is a mechanism by which we can wade through these papers, but in such a way that is not a black box solution that just gives you the answer. What we want to do instead is to make it possible for any organization that wants to do a systematic review to have a traceable pipeline by which we can sort through different types of papers. We can then figure out what the inclusion criteria to bring things in are, and then we can rank and categorize them, not just by keywords, but by location, by the intervention kind of factor that happened, by the methods used in the experiment, and make sure that as we go through all of this, we maintain a pipeline that justifies at every step of the way exactly why it took that decision. And we did this by taking advantage of Cambridge because we have licenses with all the publishers to download the data. So we actually went to the Cambridge Library and said, could we get the papers, please? And they went, which papers? And well, we said, all of them. We want all of your papers. And so after some negotiation, we got 50 million papers or whatever. And then we could put this through OpenAI models. And we also built something called a TAP, which is a traceable AI pipeline, which performs this particular service as well. And you can see how, as you build and compose these kind of graphs, you start to see an emerging architecture for these things, where you've got satellite data and indigenous knowledge. You can put them together into these multimodal systems that understand both the causative factors of literature and also the observational factors that we see from space. And then you can use that to keep humans in the loop and keep a circle going, a virtuous cycle of using the data and the evidence and then bringing it back to each other. The problem, though, is that we're starting to see some serious issues where we feed in on ourselves. So we're starting to get into a world where we're getting more and more AI poisoned papers, that is, ones that have been generated by AI, being fed into the literature. And we're also getting things like AI generated maps. And if those are then fed back into these training systems, you lose track of what is real. And before you know it, you've got a feedback loop where you're just in an echo chamber of renormalization, and then the entire system just kind of collapses. So we have a serious problem where we need to completely change the way that we manage our scholarly knowledge and our observational knowledge in order to keep track of what is real and what is not. And if we don't, and bear in mind that this whole AI wave is about a couple of years old, we probably have about a year to figure this out. And so our answer for this is to come up with something that is not just a system that lives in one institution, but to build a network, a federated network of what we call living evidence databases. And the idea is that we have multiple institutions where we can scan and ingest the millions and millions of papers that are being released every year. And we have AI pipelines that can constantly monitor and track and sort these things, including doing detection of poison. We can then use a set of data librarians, the curators around the world, who are responsible for using human intuition to figure out whether something smells wrong or if something looks like it might be the wrong kind of evidence, and then ultimately give access to this information across the entire set of organizations to make sure that decision makers have the ability to not only ask a question quickly, but to get the results in a traceable and a verifiable way. And then when they want to get a much more justification about the answers, then they can commission a full systematic review and kind of go through that work. So my argument to you here is that it is possible to build these systems. Don't give up. But we have to make a discrete choice from funders to practitioners to scientists to librarians about which pill we're going to take. The easy pill is the red pill. Just go log into Gemini and ask it, what you should have for breakfast. The blue pill is a lot more work, but it's work that if we pull it off, we can dramatically accelerate the rate at which we do conservation. We can dramatically use technology to accelerate the multiplicative force of effective actions, and we can make sure that it's equitable and accessible to the majority of humanity. So with that, I'm eager for any feedback and questions you have, and thank you for your time.